I conducted a sensitivity study on scramjet geometry, just to assess whether there is any potential benefit in variable geometry. And finally, I defined a trajectory that would provide optimal conditions for combustion. And I derived corresponding pressure recovery throughout the flight as scramjet accelerates from Mach 5 to Mach 20. Each year, we can notice that increasingly more satellites are sent into space. But what is especially interesting is that small satellites start to dominate now. Sending a satellite into space is not an easy task. We typically need a big rocket to send it into space, and that's why we send satellites in bulk. The orbit is typically determined by the biggest satellite on the rocket, which is not beneficial for small satellite providers. And that creates a need for much smaller vehicles that would be more efficient and would fly more frequently. And that creates a perfect opportunity for a scramjet. So what is a scramjet? A scramjet is a revolutionary type of a jet engine that is very simple in its principle. It has no moving parts. It has no compressor nor turbine. It achieves compression via a series of shocks generated by an inlet just by its geometry at supersonic speeds. Scramjet consists of just, let's say, 4 parts. There's an inlet, as I mentioned. Its purpose is to provide sufficient compression for combustor. Isolator, I'll discuss it in a moment. And the combustion takes place in a supersonic flow. And then nozzle is used for expansion just to maximize the exhaust velocity and maximize efficiency. Comparing scramjets to rockets, you can see that they're much more efficient. In this case, to assess that efficiency, we are using specific impulse. This is a standard metric to assess efficiency of propulsion. You can see that scramjets in low speeds can be even 10 times more efficient than rockets. And there are 2 types of fuels we use for scramjets. Most commonly hydrogen fuel, since thermodynamically it's the most powerful fuel. It also has the shortest reaction times, which are very important in scramjets. But it has a big drawback. The problem with hydrogen is that it has very low density. It takes a lot of space and then it requires very big tanks, which create a lot of aerodynamic drag. For that reason, hydrogen is preferred in space applications at very high altitude. However, hydrocarbon fuel is much denser, but it's a bit weaker and it takes a bit more time to combust. And that fuel is used typically for missiles, for military applications. And because of complexity of that fuel, their operation is limited to Mach 10, as you can see in the middle of that plot. Okay, moving on to historical perspective. The concept of scramjet is actually quite old. It dates back to 1950s. And the first major test took place in 1967. It was a hypersonic research engine. Let me see if I can hide this. All right. A hypersonic research engine was the first major scramjet that was installed to a famous X-15 aircraft. The aircraft was rocket boosted. It was accelerated to speed of Mach 6.7, and the test provided a lot of valuable data for further research. It's interesting that it was a crewed flight. The crew was on board, and on that day, a world record was set up for fastest crewed aircraft ever flown. From 1967, this record hasn't been beaten yet. The aircraft suffered from major aerodynamic damage. As you can see in a picture here, the aircraft basically caught on fire. It was going so fast and it created so much drag that some of the surfaces started burning. The main finding from that test was that the engine basically created more drag than thrust. So the conclusion was that instead of being like a separate structure, it should be integrated into airframe of the aircraft so that the drag could be minimized. After termination of that program in 1968, there was a National Aerospace Program in years 1983 to 1996. The program was extremely ambitious, and the scientists were planning to develop a vehicle, a scramjet powered vehicle, and that would be single stage and would deliver payloads to orbit. So it would have to achieve speed of Mach 25. And the program turned out to be overambitious and not feasible, mainly due to limited testing capabilities. Back then, there was no wind tunnel that could operate beyond speed of Mach 7, and also testing in flight was extremely expensive. For that reason, then the program was cancelled with not much success. However, all the data from tests and simulations was used in further research. Then in 2004, NASA has flown its X-43A scramjet vehicle. It set up a world record. It was operating for 12 seconds and it achieved peak speed of Mach 9.6. This is an official record of an air-breathing engine. To date, no other aircraft was flying faster. And then the final test vehicle was Boeing X-51 Wave Rider. That aircraft had totally different strategy. All of the previous aircrafts that I mentioned were utilizing hydrogen just to maximize that efficiency and get the highest possible speed. The X-51, however, wanted to show that a long duration flight is possible. It was flying for over 3 minutes, specifically 210 seconds, with a speed of about Mach 5. Ultimately, it has shown that scramjet flight is possible. However, until today, US has never developed a fully operational scramjet. The only country that have achieved that is Russia. Last year, they announced a missile that is capable of speeds up to Mach 9. So, what are the real challenges of scramjet? And why is it so difficult to develop a fully operational scramjet? The first problem is that conditions continuously change. As scramjet accelerates, the shocks become more stronger and they also have different angles. As scramjet accelerates, this entire shock pattern moves to the right. So correspondingly, we can expect that the number of shocks will be less because there's just less space. But when the scramjet decelerates, the shocks move to the left, and in particular, when this first shock misses that lower body, some of the air that is compressed does not go to the inlet. It's not necessarily a drawback, because this air that is lost, it provides lift. However, it impairs combustion efficiency. Now, the second serious problem is that the altitudes at which scramjet can operate are very limited. The gray area presents so-called flight corridor. Above that area, scramjet cannot generate sufficient lift, nor provide sufficient compression for efficient combustion. And below that area, the scramjet experiences excessive aerodynamic, structural, and thermal loads, and will possibly just burn up, just as you have seen in case of X-15. Another problem is that if you look at the lines of constant mass flow rate, these are the colorful lines, you can see that as we follow flight corridor, the mass flow rate decreases, which means that at higher speeds, the scramjet would generate less thrust. Another problem. Typically, at speeds beyond Mach 5, the flow is fully supersonic. That means that combustion can take place in supersonic flow, which is very efficient. However, in a flow that normally would be supersonic, the increase in pressure, in back pressure from combustion, can create a normal shock wave between an inlet and the combustor. And if that normal shock moves into the inlet, it impairs the inflow. This is known as inlet unstart. It is very undesirable phenomenon. It doesn't mean that the scramjet won't operate. It will operate, but its efficiency will be very low. So for that reason, between an inlet and combustor, we have like intermediate duct with a constant cross-section area. This is called an isolator. An isolator serves its purpose is to be like an intermediate stage that will mitigate that pressure difference. And that pressure difference is mitigated via a series of normal shock waves. This is known as shock train. And between each of these shocks, the flow accelerates, and then across the shock, it decelerates. And this is known as operation in dual mode. Since it's not fully supersonic, it cannot operate in scramjet mode. Sometimes it just has to operate in ramjet mode. What are other challenges of scramjet? There are many, there are multiple. A very important one is mixing and combustion efficiency, and especially time. It takes just a few milliseconds for air to travel from front of the combustor to the end. And within those few milliseconds, air has to mix with fuel and combust. That's why in high speed, hydrogen is the only possible fuel. Air dissociation problems. The temperature at which air arrives to the combustor has to be within specific range. If it's too low, combustion won't occur. If it's too high, air starts to dissociate. Particles of oxygen and nitrogen dissociate into single atoms, and at even higher temperatures, they can dissociate into ions and electrons. And this obviously impairs combustion. Aerodynamics and flight control within hypersonic flow are very difficult to model. And as I mentioned previously, simulation and testing capabilities are very limited even today. The fastest wind tunnels can achieve speeds of up to Mach 10, but only for something on the order of a few milliseconds. Um, longer duration tests can be achieved only with Mach numbers of about 5, 6, 7, but still it's only like 200 milliseconds. Okay, moving on to the detailed literature review. Kwan et al. Searched for an optimal 2D inlet geometry for a scramjet that would operate between Mach numbers 5 and 10, following a constant dynamic pressure trajectory of 50 kilopascals. They focused on external internal compression inlets. I'll explain that in a moment. And then they based their model on oblique shock theory, a very simple model. And they investigated performance of multiple ramps in an inlet. They determined that the optimal one would be a free ramp inlet. They also stated requirements for rapid hydrogen combustion. They stated that generally combustion time decreases with increasing pressure and temperature. And they stated that minimal static pressure should be 50 kilopascals and the temperature should be at least 1000 Kelvin. And they also validated the results against CFD simulations and achieved very comparable results, differing by just a few percent. So here's an example of external internal compression inlet. As you can see, most of the compression happens sort of outside of an inlet in the exposed area. And there's a bit of compression going on in the internal area. This is the most common layout for scramjets. And typically scramjets are designed for one specific Mach number, known as design condition. They are designed in such a way that all of the shocks meet in a single point at the tip of the cowl of the lower body. All other Mach numbers are known as of design condition. Then Dale et al. Created a very advanced tool known as Samurai software that includes not only oblique shocks, but also expansion fans and boundary layer. So it includes effects of viscosity. And this software allows them to provide very accurate results within very short time. Testing of one geometry takes just 3 seconds. And that was on a personal computer about 5 years ago. So even today, that would be faster. And then with that software, they conducted optimization of geometry based on pressure recovery. They wanted to maximize pressure recovery. And they have shown that variable geometry is superior to fixed geometry for every of design condition. And according to their study, the most efficient geometric parameter is vertical cowl displacement. In other words, the inlet height, the height of that lower body. However, rotation of the lip of that lower body can only impair performance and should be kept fixed. Again, Dale, but in another study, investigated minimal fuel consumption trajectory. He has shown that for scramjets, the constant dynamic pressure trajectory is nearly optimal. However, for dual mode, when those complex shock pattern occurs, the optimal trajectory is more complex. Here's an example. The dual mode occurs between Mach 4.5 and Mach 7. And you can see two trajectories. Trajectory A is a trajectory with no constraints. And so it can be described as following approximately constant dynamic pressure of 55 kilopascals. And then at some point, defined here as 6.4 Mach number, and Scramjet transitions from dual mode to Scramjet mode. And then trajectory B has imposed constraints here on the left side and on the right side. So now is a good time to state the objectives of my thesis. The main aim of my thesis was to assess the advantages of variable geometry for scramjets. And my main objective was to create a Python code that would be able to simulate and visualize flow field for very simple geometries. I also wanted to validate code against existing results and investigate the effects of geometric variation, how specific geometric parameters affect pressure recovery. And then I wanted to examine effects of flight trajectory on pressure recovery. Very briefly on my methodology. My methodology is based on Inviscid quasi 1D flow. What it means is that between shock waves, flow is uniform and has specified direction. As you can see, here is an example of a plot generated by my code. And you can see that between shocks, the colors are uniform. Colors correspond to specific values of properties. And with my code, I can generate plots showing variation of several properties like Mach number, static pressure, static temperature, air density, and total pressure. Within my model, I only investigated shocks, their interactions and reflections from the wall. I ignored expansion waves due to their complexity. Here are the geometric parameters that I varied. There's an inlet height.
Question, Maciej? Question?
Yes, Professor?
Are all of these properties constant, just like the Mach number between shocks?
Yes, that's my assumption.
So I just wanted to make sure because I have a question for you later on.
Yes, okay.
Go ahead.
All right. So geometric parameters. Inlet height, denoted with H. Offset of lower body, denoted with O. Horizontal wedge length, lower and upper. And all those lengths were normalized so that the inlet and isolator length in total is 1. And then I had two angular parameters, the wedge angle, upper and lower. So once again, here are the symbols indicating each of those parameters. I set up a baseline value. I created a geometry just for further analysis. It's an arbitrary geometry. And then in my sensitivity study, I varied each of these parameters, starting from baseline values, one at a time. And I investigated how it affects pressure recovery. I imposed a constraint on my trajectory. Instead of using constant dynamic pressure, as it was the case in previous studies, I imposed a constraint on static pressure within combustor, just to maintain steady combustion. The results. First of all, I validated my code against NASA shock software that is also based on oblique shock theory, and I basically achieved identical results. They only differ by a rounding error. In terms of variable geometry, the main finding from my study was that the angular parameters, the angles of wedges, can very precisely control pressure recovery. They affect it gradually, whereas all other parameters, the length parameters, affect pressure recovery discontinuously. They can only create or delete shocks. And what I mean by that, here's an example of an inlet height. What effect inlet height has on pressure recovery? It looks like steps. So when it's horizontal, it means it has no effect on the pressure recovery, right? But there are discontinuous changes, and those changes occur when new shocks are either added or subtracted. This is a very intuitive result. If you look at the plot here, imagine what happens when you decrease the height. Well, all the angles remain the same. The strength of shocks does not change. So the pattern basically remains the same, and that's why we got that we get those horizontal lines. However, if that shock pattern is kind of squeezed, it can create space for more shocks, and more shocks can create on the right. And that's why with increasing inlet height, pressure recovery can increase discontinuously. And that's the case for all of the length parameters. For angular parameters, on the other hand, we achieve curves. And because they are curves, we can control pressure recovery precisely. This dotted line connects maxima for each of the curves. And if you look closely, you can notice that those curves are essentially the same. This is the same shape, it's just stretched and translated. So actually, if we could stick to that middle wave here and always seek the maximum of that curve, we could achieve a very smooth transition, very smooth change of properties within the flow field. It's very important that we stay away from those discontinuous changes, because a sudden change can create instability, and that could be very dangerous for a scramjet. Now, focusing on the trajectory, I have examined my baseline geometry. That was a fixed geometry. Once again, with these parameters, inlet height of 0.2 and so on. And with fixed geometry, some of the discontinuous changes are inevitable. As you can see, the scramjet deals pretty well between Mach 5 and Mach, let's say, about 9.8. It's also above the dotted line. The dotted line represents constant dynamic pressure of 100 kilopascals. That is very good. However, above Mach 10, the trajectory, the aircraft will have suddenly to descend by about 8 kilometers. This is not feasible. And also another problem is that because it's below that dotted line, it would suffer from very excessive structural loads. And the corresponding pressure recovery is plotted. As expected, it drops with Mach number. And unfortunately, beyond Mach 10, it's below 50%. That is very bad. That is very inefficient. So the question is, can we improve pressure recovery? Well, we could potentially change the upper wedge angle, which has the greatest effect on pressure recovery. And you can see that as the angle gets smaller, those curves rise, okay? For example, for 3 degrees, the pressure recovery does not drop below 50%. That is great, but the problem is that with better pressure recovery, we don't achieve sufficient compression. And therefore, the aircraft would have to fly at very low altitudes. It would experience even more severe loads, and it would certainly destroy itself. Now, looking at flow properties, how they change when the baseline geometry travels from Mach 3 up to Mach 20. You can see that at the speed of Mach 3, a normal shock occurs, right? So the flow after normal shock is subsonic. Supersonic combustion cannot occur, therefore a scramjet cannot operate in scramjet mode. Then at higher speeds from Mach 4, the flow is fully supersonic. In fact, when the flow enters the isolator, no further compression is achieved. The shocks that you see here, they're actually minimal and can be as well ignored. You can see that the colors, whether it's in this plot or in this plot, within the isolator, the colors does not change. So that means that the flow maintains its properties and nothing changes. So as I mentioned, these shocks in the isolator can be ignored. Now you can see that if you count the number of shocks before the isolator, there's let's count up intersections. There's one here, second here, and third here. But now as we accelerate, that number decreases. There's one intersection here and one intersection here. That means that at some point between Mach 4 and Mach 5, one of the shocks disappeared. And that created a discontinuous change that you can see here. As I said, between Mach 4 and Mach 6, we have discontinuous change in trajectory and correspondingly pressure recovery. Now, as we accelerate further, we still have 2 intersections. But here, now we've got only one intersection at Mach 12. Notice that when the shocks reflect within the isolator, we don't count the subsequent shocks, right? Here is right at the edge, but it's still within inlet, and here then reflections are within the isolator. So here, instead of 2 intersections, we have only one. And that means again that between Mach 9 and Mach 12, another shock disappeared, which corresponds to this discontinuous change. And beyond that, transition is very smooth. The change of properties is very smooth, and that's because from Mach 12 up to Mach 20, there's only one intersection. Just to get it clear, the combustor begins right behind the isolator at X equals 1 in that right boundary. So if we look at the variation of other properties, this time the blue line represents altitude, represents the trajectory. The red line represents corresponding temperature at the combustor entrance, right? At x equals 1, exactly in that right boundary. And mass flow rate is represented by green dotted line. You can see that up to Mach 10, the operation of Scramjet is very nice. This is the flight corridor I mentioned previously. So we are at the lower boundary. That's very good. But beyond Mach 10, Scramjet suffers from excessive loads. Combustor entrance temperature is very good. At Mach 10, maybe 9.8, when rapid combustion is necessary, the temperature is just above 1000 kelvins. This is very good. That would allow hydrogen fuel to combust very rapidly. But the main problem is with mass flow rate. You can see that if we limit our operation from Mach 5 to Mach 9.8, within that operation, mass flow rate decreases 3 times. That means Scramjet would generate 3 times less thrust. And that would have to be mitigated with variation of geometry, preferably with inlet height. Imagine, for example, looking at this plot, that inlet height increases. When it increases, there is more capture area, and the inlet could capture more air, more mass flow rate. And then comparing it to the results of aforementioned studies, when we compare my results to Kwan et al., flow properties are very similar. Note that I had imposed a constraint on static pressure. That's why it's 100 kilopascals. It's very similar to the results achieved by those researchers. And surprisingly, pressure recovery is very, very similar. And also static temperature shows that near Mach 10, the temperature is sufficient for rapid hydrogen combustion. Comparing my study to Dahle et al., I'm using a much simpler model. It is not as accurate as their model. However, the results are comparable. But the conclusions seem contradictory. And why is that? In their study, Dahle et al. Stated that inlet height is the most influential parameter on pressure recovery, whereas the rotation of the cowl, the angular parameter, is the least influential. In my study, it's the opposite. Now, why is that? Well, in fact, we investigate different kinds of geometries. So looking once again at external, internal compression, you can see that for most of the speeds, at low speeds, the so-called air spillage is the problem. Air spillage occurs when that shock misses the cowl, and as I mentioned, a lot of compressed air does not get into the inlet. It goes below the scramjet. In their study that was investigated, in their study they considered the mass flow rate into the efficiency. I didn't, and for that reason, the inlet height in their study is very important. And in terms of cowl lip rotation, well, let's imagine what happens when you rotate that part. upwards, for example. It pretty much only creates drag, and that's why they stated that it impairs performance. In my case, I did something different in terms of cowl lip. I didn't rotate the entire element. I only changed that angle. And as a result, it didn't create much more drag, but it provided much more compression. And that's why it has so much influence on the performance of my scramjet. And then comparing it to the second study of Dale, focusing on the trajectory, the constraint I imposed on my scramjet brings no advantage in pressure recovery. And the scramjets, in fact, should operate at lowest possible altitude just to maximize temperature and pressure within combustor. But obviously, they have to stay within structural limits. So the conclusion is that scramjet is a very promising technology, but it's extremely challenging. United States has not created a fully operational vehicle, but that's going to change very soon. Right now, scramjets are utilized for military purposes only, but that's going to change very soon. I'm sure that within a decade we can expect civilian applications such as delivery of spacecraft to orbits, or even commercial hypersonic flights. Imagine that between any 2 points on Earth, you will be able to travel within just 2 hours, maybe even 1 hour. So as part of that thesis, I developed a Python code that is capable of simulating flow field through a simple 2D scramjet geometry. I assessed the benefit of using variable geometry. I considered only single ramp internal compression inlets, and I varied 6 geometric parameters and investigated their effect on pressure recovery. And correspondingly, I plotted trajectory and pressure recovery for any Mach number between Mach 5 and Mach 20. The main finding was that angular parameters could be varied just to determine the very precise properties in the flow, whereas the length parameters could be used to ensure that the number of shocks within an inlet is constant, and that would ensure smooth operation. For the baseline geometry that I tested, it was shown that it cannot operate beyond Mach 10. However, up to Mach 10, it would operate very well. And preferably, I would use hydrocarbon fuel, and I believe that that geometry and that fixed geometry could be utilized for missiles. For the future work, I certainly would expand this thesis with optimization. I provided a very good foundation for optimization. I investigated the effects on pressure recovery, and now I could develop a mathematical model that would maximize pressure recovery throughout the flight. I could also increase the fidelity of the model. I could certainly include the effects of expansion waves. However, they'll be quite complex. And with regarding to trajectory and to determine an optimal trajectory, I could expand my model by including combustion effects or even flight dynamics effects. Thank you for your attention, and I am awaiting your questions.
Well, thank you very much. Do you want to quickly introduce your guests?
Sorry, my what? My guests?
Your guests.
Uh,
The others on the Zoom. Are these family members, friends?
yes, let me see. Yes, they are my parents. I hope they are still connected. Yes, both of them are still connected. And there's my friend from Poland, Wojtek.
Great. Well, welcome. Glad you guys could be here. It's one advantage of having these done via Zoom is that makes it easier for people not in Chicago to attend. So
Oh, yes,
any questions from family and friends? Going once, going twice?
I guess they are shy.
Yeah, they're shy. All right, so we'll ask them to leave the Zoom
Okay.
call, and then we'll go to the committee.
Okay.